All right. So, math and cats. Enough said, right?
Sure.
Love at first sight. So, just kidding. Freya is an independent game developer and educator, and today she's going to talk about a topic that to some is the stuff of nightmares, and to others, like myself, is perhaps a little bit more the stuff of dreams and all the squiggly lines in between. So in her talk, she's going to hopefully inspire you all to consider the math underlying our games a little bit more magical.
Thank you. Okay, hello everyone to probably the most technical talk. I'm going to teach you all about set theory and quaternions. So this talk is called Why Can't You Multiply Vectors? So I've been doing a lot of things within game development and math for a long time now. I started out as an environment artist, and then I moved into level design, and then I eventually learned programming, and I got really excited about that. And then I got into math very heavily the past 2 years or so. And now I've sort of dived so deep into math that sometimes the stuff that I talk about, game developers are like, oh, this just seems like useless, abstract nonsense. Why are you even doing this? I just want to make a game. I just want to copy paste my math from the internet and just paste it into my game so that it works. I don't care about the underlying stuff. But today I want to talk about that underlying stuff anyway, so you're going to have to suffer through that. So there's a bit of a schism sometimes between math and programming. So I sent this tweet at some point on 9/11 of all days, so this is my personal 9/11, because this started a war between programmers and math people, which was really weird. But all the math people were like, what are those for loops? That makes no sense. All of these symbols, that looks so complicated and weird. And then you had all of these programmers that were like, well, what are those weird symbols? There's no context for this. There's nothing describing what that does. You just have to know what that does, right? But so all I really wanted to do was kind of draw this simple analogy for people who might not know that much math, to just be okay, so these summation symbols is just adding things up in a for loop, and the capital pi is just a product. You're just multiplying things together. And so that was interesting, because it kind of illuminated to me that there's this big schism or big divide that I kind of want to merge, and I see that as sort of my job in a way of trying to bridge that gap. A little bit about me. You probably don't care that much. Co-founded a studio called NeatCorp, made a game called Budget Cuts and Budget Cuts 2. We were a studio of 7, very awkward size. Made some plugins for Unity, one called ShaderForge and one called Shapes. One is a shader editor, and the other one is a vector graphics plugin. Then I'm also working on a spline plugin right now that is not released yet. I also make YouTube videos, so I made some videos about tech art, math, and tool development, mostly within Unity. And then I've also made some YouTube videos about Bezier curves and splines. All right. So I'm a tech artist. That's kind of the center of what I do. It's kind of the intersection of art and programming, and math kind of comes in there to do all of these kinds of weird, funky, techy visual solutions to problems in games. So a lot of the stuff I do is just trying to work out things like, how do you render lines in a way that looks nice? Because you have a naive implementation, might look like garbage, but if you spend some time thinking about it, you can make something that looks much, much prettier. And so a lot of the work that I've been doing as of late has to do with splines. This is an excerpt from my video. It's just a lot of splines. I've just had splines in my head for the past 3 years, and I can't get them out, and so here I am. Recently, I've been getting into quaternionic splines, which is splines in quaternion space to interpolate orientations, and some torsion visualizations. I don't know. I have a bunch of things related to this that I do. That's a dodecahedron. Anyway, so in this talk, we're going to explore why can't you multiply vectors. And I think, as with any other talk, I think you should always start on the second slide with some common criticisms of the title of the talk. And so some common criticisms might be, yes, you can. It's called a dot product. What are you talking about? Or you might say, well, yes, you can. It's called a cross product. Why do you mean you can't multiply vectors? Or you might say, what do you mean? I multiply vectors all the time. This could be early signs that you might be a shader programmer. And no, you're actually not really multiplying vectors. And you're going to find out why. So the anatomy of a vector, just to go through what we're actually talking about. We usually write it in bold letters, and that's a vector v. It has 3 components if it's a 3D vector. Realizing I'm forgetting to breathe, because I have so much to talk about. So we have 3 components, x component, the y component, and the z component, usually written in a parenthesis, right? And you can also write it as a column matrix if you want to, which can be useful sometimes because you can write longer lines for each component. It's kind of useful. And this kind of presumes a basis, as in the basis vectors of our coordinate system, right? We have an x-axis, we have a y-axis, and a z-axis, and they're all orthogonal to each other, and they have a length of 1. So they're orthonormal, is what we call it in the industry. All right, so products. We obviously know about the dot product. Everybody's heard about that, and it's some kind of multiplication, right? You have your vector A, your vector B, and then you write a little dot in between, and then the dot product is basically multiplying each of the components and then adding them all up into a single scalar value. So it's sometimes called a scalar product. You can also write it using the summation notation, so it's like dimension independent. So if you want to do the dot product in any dimension, you can use that formula. I hope it's readable and not too small. Then we have the cross products. The cross product does not return a scalar, it returns a vector. So the cross products, we have this kind of complicated formula of just picking out very specific components for each of the x, y, and z components of the final output vector. That's a cross product. And then we have the 2D quote-unquote cross products, which is illegal. Don't tell your math teacher that you've been using a 2D cross product, because it doesn't really exist, but it's a very useful thing in games to have. And that's basically a cross product where you just set z to 0, and then whatever's left is your 2D cross product. It's also sometimes known as the perpendicular dot product, or the exterior product, or the determinant, or the wedge product, or the antisymmetric product. It has many names. I don't know why. It's annoying. And then finally, we have the Hadamard product, which is the shader programmer product, where you just say, well, just multiply the components. Like, just do that. Like, why not? Just take every component, multiply them together. That's your new vector. So that's a component-wise product. OK, so we have the dot product, we have the cross product, and we have the Hadamard product. But what about the product? Like, just smash them together. No goddamn symbols in between, just a canonical product, right? Because usually you don't write anything in between. If you want to write 5x, you don't have to write a symbol there. In math, you just have no symbol, because multiplication is kind of the canonical main operation, right? And so I think a lot of people, me included, a few years ago, I was just like, just do it component-wise. Like, why are you overthinking this? Like, if you multiply a vector by a scalar, like a vector, like 2 times a vector A, you just multiply each component by 2, right? So that's component-wise. If you divide it by 2, that's also component-wise. If you add 2 vectors, that's also component-wise. We add the x-axes together, we add the y components together, and the z components together, also component-wise. Subtraction works exactly the same way. So why would multiply not just be the Hadamard product? You just take each component and multiply them together, right? Just don't worry about it. Just go ham. Just multiply all of your vectors and don't care about the rest. It's going to be fine. But it's not that simple, unfortunately. So I'm going to take you all back to elementary school. I'm going to talk about the natural numbers. So the integers starting from 0 and up. So all of the positive integers, and usually 0 as well. That's when you count things. So we're gonna count snail cats. So here's a snail cat. So let's say you have 2 snail cats. And then you add 3 snail cats. How many do we get? We get 5 snail cats. Isn't that amazing? So 2, 3, and 5 are all natural numbers. We can count items using natural numbers, right? So let's try multiplying. So 2 snail cats multiplied by 3 snail cats is 6 snail cats. Great. That's perfectly fine. Just one more. So we have 2 snail cats minus 3 snail cats, and then we get, well, that's not actually a natural number anymore, right? Like 2 minus 3, now we get something negative, and that's not within the realm of natural numbers. Like negative is not a natural number, right? And so in a very technical sense in math, we usually say that natural numbers are closed under addition and multiplication, but it's not closed under subtraction, because it's possible to leave the realm of natural numbers if you subtract, right? Because 2 minus 3, not a natural number. OK, so we can talk about numbers of different kinds, right? Natural numbers, we can add them. That it's closed under addition. We get a natural number if we add 2 natural numbers. Same with the multiplication, but not subtraction, because then we need the integers. The integers, they have these like technical symbols, the blackboard bold. So natural numbers are n, integers are z, for some German reasons, I think. I don't know what it is. So then we need integers, and that includes the negative numbers, right? The negative integers. OK, so integers are closed, right, so subtraction of natural numbers gives you integers. Integers are closed under addition, multiplication, and subtraction, but not under division, right? Because if you do 1 divided by 3, that's not an integer. We've left the realm of integers, and we've gone into the realm of rational numbers. So rational numbers is an integer divided by another integer. So with division, with natural numbers and integers, we get a rational number. We can also do exponentiation. So if you take like a natural number, like 2 to the power of 3, that is also a natural number. So we stay with the natural numbers there. So it's also closed under exponentiation. But integers are, again, if you do integers and you do powers on those, so like 3 to the power of -1 would also give you a rational number. All right, rational numbers, closed under addition, multiplication, subtraction, division. You get a rational number out of that. You don't change the kind of number. Exponentiation gets a little bit more complicated, because you could do to the power of 0.5, which is a square root, because 0.5 is just 1 over 2. And so then we need the real numbers. So the square root of 5 can't be expressed as an integer divided by an integer. But the real numbers are closed under all of these 4 operations. But then we might want to go to the next step. Like, what about exponentiation? And here's where we enter complex numbers. Because now it's getting a little bit weird here, because that's just an entirely different type. Because a real number is just all the usual numbers we're familiar with. But the complex numbers can express things like the square root of -5. In real numbers, we usually say that you just can't do the square root of a real number. But with complex numbers, we have a way to express that. And complex numbers are algebraically, so complex numbers. How many of you know what complex numbers are? Raise your hand. Quite a few. OK, so I can sort of speed run this one. OK. So let's say we have a thing called I. And if you square I, you get -1. It's just an algebraic symbol. It's a variable like any other. But the only thing we know about it, we don't know its contents or its value. The only thing we know is that it squares to -1. In other words, if you multiply it by itself, we get -1. And this is called the imaginary unit. And this is just axiomatically true, which is math speak for because I told you so. It is true. And we just have to accept that, right? OK, so how do we do math with this? Well, if we have 3i times 2i, that would be 6i squared. And since I squared is -1, this is equal, because we can apply this rule of I squared equals -1, then this becomes -6. OK, another example, 2i times 4i minus 3. We just distribute that, and then we get 8i squared minus 6i. Again, I squared is -1, so we get -8 minus 6i. And we can sort of think of these numbers as having 2 parts to them. The first part here is the real number. This is just a regular-ass number that we use all the time. And then we have a coefficient of I. So this is called the imaginary part. And you can kind of divide these up into these two separate categories. And that's what's called a complex number. So that's when you have a regular number, a real number, and then some coefficient of I. OK, so let's say we have a complex number z. Then we can interpret it similar to a vector, because a vector also has two parts, right? If you have a 2D vector, you have an x component and a y component. Similarly, we can write complex numbers the way we write vectors, just in parentheses, right? Where we have the real part and the imaginary part. And now the basis is just the value 1 and I, because those are the things we multiply each of the components by in order to get the final result, right? So you can kind of see the similarity between complex numbers and vectors. Like, they both have two components, well, for 2D vectors. And so you can define a coordinate space using vectors. You have an x-axis and a y-axis. You can also just do the same with imaginary units. So you can have a real axis for the real numbers, and a vertical axis that's the imaginary axis. And then for writing coordinates, we just do exactly the same thing we do for vectors. So for 2D vectors, we have maybe this coordinate would be 1 and 2. So 1 on the x-axis, 2 on the y-axis. Can do the same for the complex numbers. So this is called a complex plane. And it's just the same. It's just 1 and 2. It's just that we're using a different basis. The cool thing about complex numbers is that we can actually just write them as a formula, like the way we did before, just 1 plus 2i. That's what this represents, right? And so this is really useful. What's useful about this one is that we can do algebra with this. If we have this formula, we can just add them together or multiply them and just see what happens, right? And so if we wanted to find out, like, OK, what happens when you multiply two vectors? Well, if complex numbers are vector-like, we can figure out what happens when you multiply two complex numbers. And maybe that's going to give us like some answers along the way for how to multiply vectors together. So we can just try to go through that process. So like, let's say we have two complex numbers, a complex number a and b. We multiply those together. So we just write them out as equations. And as usual, we just distribute or like expand the whole thing. Then we might notice that, oh, this part has two i's in it, right? So it's I squared, which means that it's equal to -1. So we multiply that whole thing by -1. And so now we can see that this part, they share a common factor of I, so we can factor that out. And now we get a complex number in the end. So we had two complex numbers. We multiply them together, just regular multiplying, no dot products or cross products or anything. We just multiply them together. And in the end, we get another complex number, because we can express this as a coefficient of just a real number and a coefficient of I. So what we can say is, again, complex numbers are closed under multiplication because we give two complex numbers and we get a complex numbers out of it. So if you want to implement this in code, like, this is how you would write that. The actual symbol of I is never in your code. It's just completely not there. The I is only there to like help us define the algebraic operations that we do using this. And so we had our formula here, right? So we're calculating some sort of real part from two complex numbers. And then we get the real part here. And then we calculate the imaginary part, we get the imaginary part, and then we'll return a complex number. So we only ever store the coefficients. We don't ever store like the weird I symbol, right? So the reason we can do this is because it's closed under multiplication. That's why it returns a complex number. OK, so what does this look like? Because now, if we interpret this as a vector, we should be able to visualize this, because we can interpret complex numbers as 2D vectors. And this is what it would look like. So here we have two vectors, the red one and the blue one, and we multiply them as complex numbers in the complex plane. And the green vector is the result. And you might be able to tell that it has something to do with like sort of adding the angles up, right? It's kind of like taking the angle of one of the vectors, adding it to the other angle, and when it's normalized, you can see that the vectors have the same length. Like the green one doesn't get longer or shorter than the red one or the blue one. And so this one is, while it's not a vector multiplication, it's still complex number multiplication, we might be able to apply some of the same strategies for figuring out like what happens when you multiply vectors. OK, so now we figured out that complex numbers are closed under multiplication, and in fact, they are closed under all of these operations. And it's the only, I think it's called a complete algebra. I think it's actually the only complete algebra within math, which I think is kind of cool, that it's closed under all of these operations. All right, but what we really want to figure out is vectors, right? Like, that was the whole point of this talk. Like, why can't we multiply vectors? Like, this should be possible. I really want to try to do it, you know? So if we go back to this, we could write our complex numbers as a real part plus an imaginary part times I. So why can't we do that with vectors? We have an x component, we multiply it by a symbol representing our x-axis, and then we add the y component multiplied by a symbol representing the y-axis. And so now, if we use this, again, we can do algebra with this, right? Like, now we can actually just do it ourselves. Instead of just listening to our math teacher or me, you can just actually do it yourself, right? So now we have another way of writing vectors. In other words, like this. If we have a 3D vector, we just take each of the components and multiply them by the symbol representing each of the 3 basis vectors of our coordinate system. OK, so if we have 2 vectors, a and b, these are 3D vectors, we can write them like this. So these, again, we have the components, we have the axes, and then we can do some algebra with this. So let's do something simple, like multiplying a scalar by a vector, just a number times a vector. Well, we have a number s, we multiply that by our vector, and that just distributes to all the terms in there, and we can see that that's a component-wise multiplication, which is what we would expect, right? Because we've been told that that's component-wise, and it seems to be, right? All right, let's try one more. So addition. So if we want to add these 2 vectors together, we can remove the parentheses because they're useless. And then we can find some common factors here. There's a common factor of the x-axis. Again, the red x is just referring to the abstract concept of the x-axis. And so we just factor out those axes, and we end up with this. And now again, we have a clean factor of x, y, and z separately. And so we can say that addition is component-wise, which is what we were told before too, so I guess they were right, so that's component-wise, fine. And if we do this with all of these operations, we can find that both addition and subtraction is component-wise. But we haven't multiplied 2 separate vectors yet, right? We've only done a scalar times a vector, but not a vector times a vector. And so what's that going to be? Like, are we going to stay within the realm of 3D vectors? Kind of like the cross product. The cross product, has us stay in there, right? Or maybe we're kind of like the dot product, where we just get a real number out of it instead of a vector, right? OK, so let's find out. We have the tools, right? We can just have our 2 vectors, a and b, multiplying them together, no goddamn symbols in between, just a pure multiplication. We write it out. This is the equation we just have to solve for, right? Like a straight-up multiplication. There's a lot of terms here, because you need to multiply these together, and you get this, which is ax, bx, xx, which is a little bit abstract. We don't quite know what that is yet. And then we just keep on doing this, and we end up with a lot of terms. And so there we go. There we have it. So this is what happens when you multiply 2 vectors, I guess. But now we have a little bit of a problem. Because this is not a vector anymore. We can't write this as a factor of x plus a factor of y plus a factor of z. This is just a pile of nonsense, right? And so we can see that vectors are just not closed under multiplication. We don't get a vector out of this, it seems. And so that's why you can't multiply vectors. And so thanks for coming to my talk. Hope this was useful. And so obviously, that doesn't feel enough, right? OK, we found out that it had this weird solution, but what is it? I need to find out. We have to solve this. We haven't solved it yet. It obviously gave us some sort of algebraic structure, and we need to investigate this and actually decode this whole thing, because there has to be answers in there, right? I'm willing to go to the ends of the earth to just approach this whole problem and just figure out everything. And maybe we need to take a little bit of a leap of faith as a treat. And so we're going to ask an oracle, a divine being of incomprehensible wisdom. Oh, great Oracle Salad. His name is Salad. We made a feeble attempt at multiplying vectors, and we seem to have reached an impasse. Can you illuminate us? The divine being contemplates for a second and says, I see. A tricky conundrum indeed, but fear not. The answers you seek are closer than you think. Don't worry, you are safe now, my child. I bestow upon you a key to understanding. Venture forth, and the answers you seek will be revealed to you. Now I must nap. Leave me be. And the divine being turns into a non-Euclidean manifold. Okay, so this is some sort of divine axiomatic truth we were given. Oh, so what does this say? So it's a vector, because it's in bold. So if you multiply a vector by itself, in other words, square it, you get the length squared. Like the length of that vector multiplied by itself. But this is not the full answer, right? This is just what happens when you multiply a vector by itself, but we want to know what happens when you multiply two arbitrary vectors. Okay, but let's experiment with this. So let's say we have a vector with the values 1, 2, and 3, and we want to square this. In other words, multiply it by itself. According to our divine axiom, it is the length squared. And the length, we can just use the Pythagorean theorem, right? We've learned that in school. And then we square that. The square root and the square cancel out, and so we're left with 1 squared plus 2 squared plus 3 squared, and we get 14. Okay, so if we square a vector, we get just a real number, and in this case it's 14. Okay, so let's explore this some more. So what about our basis vectors? Because we have an x-axis, a y-axis, and a z-axis. They all have a length of 1, right? So what happens when you multiply those two together? Well, following our axiom, that should be equal to the length squared, which is just 1 squared, right? And so that's just 1. So if you take our x-axis and multiply it by the x-axis, we get 1 out of that. And all of a sudden, we actually have gotten one key to the solution here, because all of these terms that are crossed out, they just evaluate to 1. So those 3 terms are just multiplied by 1, right? Okay, so now we've started to unravel this a little bit. So now we can separate out those terms. We have that's just a real number, because those are no longer multiplied by a vector, right? All right, but we still have a bit of a mess on the lower part. What the heck is yz and xz and yx? That's still nonsense to us, right? But there's actually one more thing that our divine axiomatic rule gives us. So if you consider the basis vectors, again, mutually orthogonal, they have a length of 1, yada, yada. If you consider the diagonal between x and y, just x plus y gives you this white vector, right? And we know that the length of that one is the square root of 2, because we can use the Pythagorean theorem for that, right? And so then we can actually make use of our axiom to find out some more about this, because we can plug in the length that is the square root of 2. So if we take our vector, the white vector is just x plus y, and we square that, we should get something that is the square root of 2 squared. So the left-hand side we can expand. The right-hand side, we can just cancel out the square root. And so we get the expanded form of xx plus xy plus yx plus yy, and that's equal to 2. All right, but we know that x times x is 1, and y times y is 1, right? We already figured that out. So now we have this. We can subtract 2 from both sides. So we end up with xy plus yx equals 0. And if we subtract yx from both sides, we get this. And this might seem kind of innocent. OK, sure. We have xy equals negative yx. So the components are swapped and negated. But it means that they're equal. So we can swap components at will. Because if they're basis vectors, then we can do this. OK, so going back to our equation here, we can see that in the top one, we have yz on the first term, but then we have zy on the other one. So what we can do is that we can swap these two terms and then negate that term, because we now have this rule of xy equals negative yx. So we swap them, and now we have subtraction symbols there instead of addition. And then we can factor those out. Do any of you recognize these? Do these formulas seem familiar? Something seems to have kind of jumped out at us, right? This is the dot product. And we never set out to define the dot product. We just followed the divine command we were given of like the square of a vector is the magnitude squared. And somehow we got the dot product out of it as a complete like side effect. And this is the cross product. The cross product somehow also jumped out of us. So we just somehow invented both the dot product and the cross product without ever intending to do so. We just wanted to know what happens when you multiply two vectors, right? And so everything stems from this one rule. But we still have a mystery of like, what the heck are these anyway? Like yz, zx, xy are just kind of confusing constructs. We know nothing about them, right? So let's explore those a little further and see what happens with those. So for example, maybe we can try seeing what happens if you square them. We take xy squared. That equals xy, xy. And we know that we can swap two of these and negate, and that's going to be the same thing. So if we swap the middle two components, we get negative xx, yy. We know what xx is. We know what yy is, right? So we get negative 1 times 1. So we know that that's equal to negative 1. So we have a thing that we can square that gives us a negative 1. That's the imaginary unit. We didn't set out to invent the imaginary unit either. This is all just still stemming from that one axiomatic rule. And this actually applies to the other combinations as well of zx and yz. And so if you mash them together like this, that will all of that equals negative 1. And you might have seen this in a different form before. So I squared equals j squared equals k squared equals ijk equals negative 1 is the definition of quaternions. That's the way quaternions are defined right now. And so what seems to have happened is that when we multiply two vectors together, two 3D vectors together, we get a quaternion, which is written with an H for Hamilton. And so that's kind of weird, isn't it? And so this thing that we have here has a basis of 1, yz, zx, and xy, and that has the exact algebraic behavior of quaternions. And each component, obviously, it's a factor of each of these, so you can it's a multiple of each of those bases. And so that's our quaternions. And so what about 2D? Like, we haven't looked at 2D vectors now, so we should try 2D as well. That's just setting z to 0. And if we multiply two 2D vectors together, we get this. And this has a basis of 1 and xy, which that's the complex numbers. That still just has the same algebraic behavior as complex numbers. But so this is fascinating and kind of weird that we just like went through this algebraic journey and somehow like multiplying vectors gives us quaternions and complex numbers. But again, like what are these things? Like what is yz and zx and xy? And like we still don't know. Like we kind of want to find that out too. So if we consider the basis vectors of a coordinate system, our xy axes, or in 3D, our xyz axes, they all have a length of 1, and they're all mutually orthogonal. So that's our basis vectors. The things we're trying to figure out now are these like yz and zx and all of that, right? And these look suspiciously similar to the cross product, don't they? And the cross product has this behavior of if you have two vectors, a and b, and you do the cross product, you get something that's perpendicular to both of them. In other words, it's normal to the plane formed by those two vectors. And it also just so happens that the magnitude, the length of this green vector, is the area formed by the parallelogram between those two vectors, both in 2D and in 3D. And so maybe this has something to do with planes rather than like points in space, right? All right, so if we have our xy component, that's the only one we have in 2D. That was the one that was equal to the imaginary unit. And in 3D, we have yz, zx, and xy. So what if we conceptualize these bases as planes? So maybe our xy refers to the plane formed by x and y, and specifically the unit plane, like a plane with an area of 1. And if we extend this to 3D, there's obviously 3 planes now that are the basis planes of our coordinate system. And so maybe we can call these bases bivectors. So that's what we're going to name these. They're not quite vectors, but they're sort of like two vectors forming a plane, so let's call them bivectors. They have an area of 1, and they are mutually orthogonal. And so the way to think about this is that if you have a regular vector, like a point in space, then it's kind of like casting a shadow onto each of the axes, right? The 3 components of a vector is just how far along each axis is this point. And so for bivectors, it's the same thing, but instead of points along axes, maybe we can interpret this as an oriented area, casting shadows on each of those 3 basis bivectors, the 3 basis planes. And so a bivector has those 3 numbers. It looks very similar to a vector if you just look at those numbers, right? But we interpret it as a bivector. So it's an oriented plane with an area, and that's it. It has no position or anything like that. And if we manipulate it, you can see that the numbers change as well. So this is just me turning it around in Unity. And so again, we get kind of the shadow on each of those 3 planes. And it can be negative, so we get a signed area on each of those three planes. And obviously, it has an area, so we can scale it up as well. It can be larger and it can be smaller, and so forth. And so this is what a bivector would look like if you just write it in code. You have like just 3 components. It looks awfully similar to a vector, but algebraically, it's entirely different because the basis is yz, zx, and xy. It's not xyz. And in fact, these bivectors, they represent the minimum information required in any given dimension to store both a plane and a magnitude. And this is why it shows up quite a lot when dealing with rotations, because rotations happen in a plane, right? Like, they don't really happen around an axis. Like, if you have rotations in 2D, there's no third axis to speak of, but there is a plane you can rotate in, right? And so, if you look back at the cross product, again, gave us a vector. So it has an x, y, and z component, which is a regular vector. But the thing about the cross product is that in math and physics, we talk about something called a pseudo-vector, which is, it has like these weird transformation rules. Like, if you mirror the result of a cross product, it doesn't have the like expected behavior. And it only works in 3D and 7D. Don't ask me why. It's just the way it is. And it has all of these hidden transformation rules. The thing we were doing now, where we returned a bivector instead, is called a wedge product. And usually you write it with this little hat thing. And so algebraically, it's exactly the same in terms of the coefficients, but the bases we use are completely different, because we have yz, zx, and xy instead. So this returns a bivector. It generalizes to any dimension. It doesn't have to be only 3D and 7D or whatever. And it's a little harder to understand, though, because like, we were never really taught about bivectors in school, right? Or at least I wasn't, but. And so here we have the 3D and the 2D vector multiplication. We can write it a little bit more generalized by saying that multiplying 2 vectors together is the dot product plus the wedge product of those 2 vectors together, because the wedge product gives us the bivector part of that multiplication. Let's see, does this work? Oh shit, it works. Hell yeah. I thought internet wouldn't work. And another place where this actually shows up that I ran into is when talking about a thing called curvature. So here you can see something called the osculating circle. So this is kind of the circle that matches the curvature of this spline that it's moving along. And the radius of that is 1 divided by the curvature. So if instead of thinking about the radius, you think about the inverse of the radius, and that's curvature. So a curvature of 0 is a straight line. A curvature of 1 turns in one direction. A curvature of -1 turns in the other direction. Anyway, it's a useful concept. And so if we want to measure curvature of a parametric function, say, this is how you would do curvature in 2D. This is just like straight up from Wikipedia if you want to see how to measure curvature. This is a scalar, and it's signed. In other words, it can be both negative and positive. And then we have curvature in 3D. And here we have the magnitude of the cross product between the velocity and the acceleration divided by the speed cubed. And so these are like, these look very different if you're not familiar with everything that we just talked about. But like this one is always positive because we're getting the magnitude of a vector. So all of a sudden, it's no longer signed. There's no like negative curvature or positive curvature. And what about the axis? Like if curvature turns kind of around an axis in 3D, right? And so these two, that's still looking a little sus. Like now we can kind of recognize these patterns, right? And so this is just a wedge product. So we've kind of been mistaken in thinking about the curvature and thinking of them as like either a scalar or the cross product or the magnitude of the cross product. But if we just do the wedge product instead, that is just much more simple, and it generalizes to any dimension again. And so instead of returning just a scalar or a vector, we get a bivector out of that. Yes, I'm going to go a little bit over time. Are you all OK with that? OK, I'm almost done. So this is kind of a generalized curvature. Anyway, so what I think is cool about this is that throughout math, we've had this thing of like mental gymnastics of like, you can't really multiply vectors, but here's 8 different products. Just use those instead. And also the cross product doesn't work at all in all dimension, but it works in 3D and like 5D or 7D maybe, like one of those. And also cross product returns a pseudo vector with like special transformation rules, so it's not really a vector. And complex numbers, they're like 2D vectors, but also not at all, but they can like rotate. And quaternions are like an extension of complex numbers with the rules I squared equals j squared equals k squared equals ijk equals -1. It's just like, Jesus Christ, right? Or we can just say that if you square a vector, you get the length squared. That seems a little bit more simple. And then everything else, all of those things we talked about, just naturally emerge from that definition. What we've been talking about is called geometric algebra. More specifically, it's a Clifford algebra. And if you take all of these components and like combine them into a big multi-vector, in 2D, that will look like this. We have a scalar, or a real number, we have a vector and a bivector. Vector has 2 components, bivector only has 1 component. That's a full 2D VGA multi-vector. So VGA is either vanilla geometric algebra or vector geometric algebra. People haven't agreed on this. Then the 3D multi-vector looks like this. So the vector has 3 components now, and the bivector also has 3 components. And this is why we probably mixed up vectors, pseudo-vectors together, because like they both have 3 components in 3D. But it's actually much better to express the result of the cross product as a bivector instead. There's also a thing called a trivector, which is the unit volume formed by the 3 basis vectors. We're not going to get into that. And so basically, all of these concepts that we've kind of like juggled around with all these special rules, they can actually generalize in a really clean way using this framework, right? And so instead of like separating like complex numbers and quaternions as like separate things, we can just call them rotors, and that's a real number plus a bivector of that given dimension. And so finally, after this whole journey, you might be wondering, like, well, if multiplying 2 3D vectors gives us a quaternion, and in games we use quaternions for rotations, what rotation does that represent? Like, what happens when we do that? And this is what it represents. So we're multiplying these 2 vectors together, and the orientation that we get, we're orienting this cube based on it, is twice the angle between those 2 vectors in the plane formed by those 2 vectors. And so that applies to 3D as well. So if we like separate these 2 vectors out, you can see that the cube rotates after that. And it's like twice the angle between those 2. If you want to read up more on that, look up quaternions, a double cover that talks about why it's twice the angle. And so why couldn't you multiply vectors? Well, probably because your teacher didn't explain geometric algebra to you, right? But now you can. And that's my talk. Thank you very much for coming.
All right. Thank you so much. So if anything, your talk was both a question and an answer to the multiplication of Cath, Mats, and rainbows. So there's that. You have produced a at least an answer to that very tricky multiplication. And with that, I would love to open it up for a couple of questions. Anyone has any?
Yeah, this is a really weird cube that they pass around. It's very strange. I probably should have mentioned that there was going to be questions at the end, and now I forgot.
What are you exploring next while people think of questions?
Sorry, what?
What area are you exploring next that you want to break your brain over?
I'm still stuck in quaternions. So I've been making like a spline library, where like a spline library for Unity that has like quaternionic splines, and I want to like implement a bunch of different types of splines in quaternion space, which is really fascinating and weird. And so that's been kind of a recent obsession. Yes. Is it working?
Yeah. All right.
Oh, there we go.
First of all, I want to say I love the talk that you've been giving, and also your YouTube channel. That
oh, can you talk a little closer? I can.
Yeah. That I really like your YouTube channel and the talk that you've just been giving.
Oh, thank you.
What different type of problems do you have that could help with where you would have a benefit for using the wedge factor or these operations in? So what other type of problems?
Most of it is useless. Like if you like this whole talk, waste of time. But it's like, again, this is kind of more like reframing things you already knew. Like if you looked up how quaternions worked or how complex numbers worked, they would just be separate systems kind of, but now they're kind of unified in a way that makes more sense. Like for example, one thing that I think a lot of people, if you want to implement quaternions, most people, even engine developers, probably just like copy some code, paste it into their engine, and then call it a day, and now you have quaternion for rotations, right? But one thing that I learned after like reading up on how they actually work is like you can learn all sorts of like tricks with them. So for example, I had a use case of I wanted to like interpolate and I don't know which coordinate system we should use. I wanted to interpolate an orientation along a spline. And then I wanted to add a feature of reversing that spline. So this should turn 180 degrees in order to reverse that whole spline. And when I did the math for that, did you know that like reversing a quaternion is a swizzle? You just shuffle the components. Like you can just, and in any of these three axes or the world space axes, it's literally just shuffling the components. It's a free operation in terms of like computational power. You don't have to do a full like 180-degree angle axis multiplication, right? And stuff like that is like all of these little like mathematical tricks that kind of pop out. But if you don't really care that much about that, you don't have to learn all of this. It's just a useful framework to me, at least. And also, if you want to make a game in any other dimension than 2D or 3D, this is also very useful. Then you really need this. All right, any other questions? People are really hungry. I'm sorry I kept you all this long. Oh, over there.
You get a cube.
Thank you. And does your math library support geometric algebra?
So yeah, I do have a math library on GitHub. I have some geometric algebra components. It's not like fully fleshed out. So I've only been like adding things there as I need them. I haven't like made it into a library that has literally everything. But I do have a library on my GitHub with like there's a bivector 3 type there. And there's a like rotor 3 type, which is just a quaternion, right? But I do have that in my math library. Yeah. So if you do want to look into the code of like how this might look, my website is up there. These days there are too many social medias, so just everything's there. Just go there, and then you can find all of the links to that.
Thanks.
Oh, actually, I don't think I have a link to my GitHub there. That's the only link I don't have on my website. But you can probably find it if you Google, I think. All right. Any other questions? And also, you can, if you have other questions, like later, you can just come up to me and talk to me. That makes me feel important and happy that I could provide value to all of you. So please validate my feelings by talking to me later.
Hi. I was just wondering, do you still plan to do like your tools on other engines too? Like on Unreal Engine, for example, your Spline upcoming tool?
I've considered it, like obviously with all of the Unity disaster. I've considered it, and I looked into Godot, and I looked into Unreal, but they're very different tools. Like, Unreal is like, it's a level designer and level artist tool that turned into a game engine. And Godot is like, it's just engineers making an engine for engineers, and it's very engineer. And I feel it's not very artist focused. And then anytime I try to do something that I do in Unity of like making like quick editor scripts and just like have that really fast iteration, that is just destroyed in Unreal. In Godot, I think it's a bit more balanced because they have like a more like easy to use like scripting language and whatnot. But I don't know. Like if I make like 70% of my income is from selling plugins in Unity. And so like, could I really support that in Godot, which is like very like open source, free software driven? And I'm like, I don't know. I think that community is not like quite like big enough yet to like support something like the tools that I do. And so like, if anything, I might like transition to doing like standalone tools, just separate EXEs that you open, rather than like tying it to any specific engine. Or I'm just going to go back to making games again, because yeah, I kind of want to do that. But yeah. Yep. All right. I think we got a sign that we should cut. Yes, a stoic nod of like, all right, thank you all so much for coming. Or did you want to close out? Or
No, we're good.
oh, okay. Okay.
All right. Thank you all. Time for lunch.